Welcome to BKW Physics. I'm Mr. McConnelly. We're doing some introductory topics here in physics. Physics you often talk about in words, how something works. You describe it. You then usually show some sort of graph representation, and the people in my class here have been doing some work where you try to move your body in accordance to what the graph is showing you, so you can graph things in physics. And then you have equations, and we'll get into equations a lot more soon. All that being said, one of the introductory thing that we want to really start with is what is a frame of reference? And I got some good ways for you to think of this. Just visualize for a second, if you were to look at the Earth from a long way away. I know you've seen some sort of picture of the Earth from a long distance away, maybe from the space shuttle or from a satellite or from the moon, and you were looking back towards the Earth. The Earth would look really round. And I don't know if my picture shows that that's that round, but the Earth would look really round, just like a perfect sphere, an oblate spheroid. And that's from that frame of reference. But now, I want you to imagine you're standing at the bottom of Mount Everest. What do you see at the bottom of Mount Everest? You see this massive thing that looks basically impossible to climb because it's just so huge. But back up, because that's your frame of reference. At that moment, it's like, oh, the mountain's right in front of you. Back up and look at the Earth from a long distance away, and where's Mount Everest? Well, I'll give you a hint. You're not even really going to see it. It's like, there it is. Okay, really huge. Okay, so depending on your frame of reference is going to totally change how you're seeing the whole picture here. Now, this is especially true in physics. We don't usually talk about looking at the Earth from a long distance away, but what we do talk about are things like, hey, if you're in a moving vehicle and you're driving down the road, it just seems like the scenery is going by you like this. It doesn't seem that impressive, even if you're going like 55, 60 miles an hour. However, change frames of reference, stand right on the edge of the road and have a car go by you at 55 or 60 miles an hour. That's a really different frame of reference, and you get a totally different perspective on what's going on. Can you see what's happening here? So your frame of reference is going to make it so that you interpret a situation differently. One last example. A person standing here. Yeah, they're a huge person. Okay, super exaggerated. Another person is standing on this side of the Earth. Is one of them upside down? Well, from this frame of reference, you might say, well, that person's upside down. But if you were in this person's frame of reference, you would not feel at all upside down. It doesn't matter where you are on the surface of the Earth, you don't feel upside down. But if you back up far enough and your frame of reference changes, then what is up for this person is down for that person. You know what I mean? So up and down are a relative thing. We'll have to come back to that quite a bit. But it ties into this right here. Your reference point. Your reference point is where the measurements, where you're taking measurements from. Your reference point is where you're taking the measurements from. So if you're taking measurements from the center of the Earth, that's a lot different than if you're taking measurements from the surface of the Earth. You're going to get two different answers sometimes. Okay? Or a simpler example that other people might latch on to better. If this is a vehicle here, and this vehicle is moving this way, and your reference point is right here. This is ref point. Now if you're standing at the reference point and you're making measurements, then this vehicle is moving away and the distances are getting bigger and bigger and bigger, right? But if your reference point is not here anymore, if your reference point is in the vehicle, what's your distance going to be doing? It's staying the same. Okay, because you're just there, and you're there. The car is moving, but you're always at the reference point. So depending where the reference point is, it's going to totally change the outcome. All right. That ties into this next concept here, believe it or not, of distance and displacement. Okay. If you start out on some bicycle course, racing course, you're racing your bicycle, and like the Tour de France or something like that, and they go through towns sometimes. Okay? Now they might start here, X marks the spot, they start here, they go this way, and they take a right, they take a left, and then they come back this way, this way, this way, this way, this way, okay. And then they go out into the country and take a huge loop and come back again, whatever. The course can be whatever it is. If you're measuring the distance, you're going to get a much different answer than if you're measuring the displacement. Okay, what's the difference? Well, distance, you would say, oh, this is 2 miles here, 3 miles here, 3 miles here, 3 miles here. That's at 1 mile, that's at 0.5 miles. And you would add up the distance as you go. So when you add it all up, you get a distance. But the displacement is just how far you're separated from your starting point. So your displacement, like if you're right here at this point, your displacement is just straight line. I don't care that you rode over there, whatever. Okay, your displacement is how far you are, straight line, from where you are now. Okay? So this is your distance, or how far you are from your starting position. Now, yes?
So if you went in a straight line, distance and displacement should be the same then?
Yes, they could be the same. Okay? As long as your reference point were the same, yeah. Okay, that can be true, but in my example, I was trying to show you an example where they're really, really different, okay? One of these is a vector, and one of these is a scalar. So how does this work? Well, both of them are like how far something is, right? But one of them, the direction was really important, and one of them, the direction didn't matter. So by definition, if the direction matters, you are a vector. So because in displacement, the direction that you displace matters, you're a vector. Now, distance has a magnitude or a size, right? And so does displacement. It has a magnitude or a size. So both of them have a magnitude or a size, but the difference is that with displacement, the direction you went was of utmost importance, and with distance, we can keep changing direction, we just keep adding it on, it doesn't matter which way we're going. That's the basic difference between those two. Same thing for speed and velocity. Most of the times in English language we use these words interchangeably. Speed, velocity, yeah, same thing, same. Well, it's not the same thing. It's two, in physics, they're two slightly different things. If you have a velocity, you are a vector. And if you have a speed, you are talking about a scalar. So, do both of these have a number? Yes. 20 meters per second, 20 meters per second. See, I'll keep them the same number. So you can see they both have a magnitude. They're both the same number. In this case, it's how fast you're going. 20 meters in a second. 20 meters per second. 20 meters in a second. Fine. But one of them, the velocity, is a vector because it's very important which way you are traveling at that speed. So you could say 20 meters per second at 30 degrees, for example. You could say 20 meters per second negative. I just put a negative sign in front of that. Because now what I'm saying is, well, you complete the thought here. What am I saying? Negative 20 means what compared to my reference point? Yeah, I'm like backing up. Like my reference point is here. It means you're coming back towards the reference point. Away would be positive, back towards would be negative. So you can drive your car 20 meters per second, or you can drive your car 20 meters per second. Those are two different things if you're talking about a vector, if you're talking about velocity. Okay. One last thing to kind of wrap this up for today is, and we'll come back to a lot of these concepts over and over again. Simple equation that you've really been familiar with for a long time now is if you want to know how fast something's going, the velocity of it, the speed of it, you do the distance divided by the time. And simple equation. So, the only thing I'm going to add to it is over top of the V, I'm going to put a line, which means average velocity. Average velocity is distance divided by time. So is distance a scalar or a vector? Distance. Scalar or vector? It's a scalar. It doesn't matter which way we're going here with this. And this equation can be used for all sorts of things, and some of the problems I'm assigning for homework are going to be based on this equation. So for today, physics.